folks, let's continue our exploration of curvilinear coordinates. This is the last lecture on technicalities. We'll start with quantum mechanics applications next week. And the biggest problem that we will address today is that Cartesian coordinates are, well, simple, because the volume element dx, dy, dz is the same everywhere. However, if we look at polar or spherical coordinates, then dr, d theta, d phi, as we'll now see, actually depend on where you are in three-dimensional space. And the best way to illustrate it is to draw a system of Cartesian coordinates, x, y, and then let's say this is our area element, x, dy. Dx. This is dy infinitesimally small, and this is the little area that we are summing over when we are integrating some function of two variables. Well, it stands to reason that this little element is the same everywhere. If I translate this picture around, that's still the same little square. However, if we draw the equivalent for the polar coordinate system, and take a look at our d phi, so that's the element of the angle that we have, and then dr is something so this is our dr, then it is clear even visually that if we were to translate this area element closer to the origin, keeping the same dr and d phi, that this would become smaller. And so we have this problem in that, okay, polar and spherical coordinates simplify the function we are integrating and perhaps simplify the limits, but we must teach ourselves to translate the area elements between these two coordinate systems. At the same time, the relationship is linear, because dx, dy here and dr, d phi there must be proportionate in some way. So we do expect, and we will have a proof today, that there's something in here that connects the two, but we need to find that out. What I need to introduce to do that is something called the Jacobian matrix. Imagine we have two systems of coordinates that are connected in the following way. We have x, that is x of u, v, and so on. That y is y of u, v, and so on. And this can continue. So we can in principle have one multidimensional system of coordinates being translated into another one by some functions. Then we can build the following matrix. It's called the Jacobian, and it is this. It's dx by du, dx by dv, and so on. Then dy by du, dy by dv, and so on, and continues. Now, there is a theorem which we unfortunately in this course do not have the time to prove. I don't think it's even in Steiner, but you can look it up in the deeper mathematics textbooks, that dx, dy, and so on is connected to du, dv, and so on. So the volume element of this space is connected to the volume element of that space by the determinant of that Jacobian matrix. And we will use this, so this is given without proof, and we will use this today to establish these connections. So let us try this out for polar coordinates. Well, first let us think about what we actually expect. Notice that this becomes bigger when the r becomes bigger. Right, so the element dr is the same at all angles, but as we move further with r, this increases. So we expect this connection to be at least proportional to r. Let's find out if that's actually the case. Polar coordinates. So polar Jacobian. Well, we need to calculate all the partial derivatives. How j will be dx by dr. Well, for that, let's remind ourselves what the coordinates have been. X plus r cosine phi and y is r sine phi. So here x and y are x and y, but u and v are r and phi. So dx by dr, dx by d phi, dy by dr, and dy by d phi. This is our Jacobian matrix in this case. Okay, dx by dr is cosine phi. Dx by d phi is minus r sine phi. Then dy by dr is sine phi. And then dy by d phi is r cos phi. Let's take this determinant. Well, the standard product are cosine squared phi and then minus because of that are sine squared phi plus r. Therefore just r. And so we conclude that in polar coordinates, dx, dy is r, dr, d phi. This is very important, and I need you to never forget this. Let's go through an example of a function that is clearly too horrible to be integrated in Cartesian coordinates, which we will need to translate into polar coordinates using that relation over there. Incidentally, I've solved our squishy board problem as well. Okay, so integrate example. Integrate f of x y equals 1 over 1 plus x squared plus y squared over to the unit disk. Okay, so the integration area is quite simple. We have x, y, and the disk with a radius. Now let us think about what would happen if we were to try integrating this in Cartesians. We have our double integral over this, and it is dx dy over 1 plus x squared plus y squared. Okay, well, let us take an integral first with respect to x, and it will clearly be from -1 to 1 with respect to x. But then at each x, we will have to integrate from the top of this circle to the bottom of this circle. And this circle is x squared plus y squared equals 1, right? The unit of disk. And therefore, it's -1 to 1 dx, but we will have to x equals plus or minus root 1 minus y squared, or equivalently, y equals plus or minus root 1 minus x squared. And so because the second integral is with respect to y, we will have to put in the x limit from minus root 1 minus x squared plus root 1 minus x squared. All of this apply to this function here, 1 plus x squared plus y squared. Well, as you can plainly see, this is not a good idea. A, it's utterly unclear how to integrate this with respect to y alone, but not x. We would have to find some splitting to make sure that that's something that only involves y. Then the integral is going to be a logarithm. Then we will have the logarithm of the torah, and it will be just a mess. Let us instead try and do that in polar coordinates. So the same integral here. Well, this is a complete disk, so phi goes from 0 to 2 pi, and r goes from 0 to 1. And then let us translate that as well. Okay, so that will be then an integral from 0 to 2 pi d phi, then an integral from 0 to 1. Now, because dx dy is r dr d phi, this is r dr. And then let's take a look at the function. It is 1 plus r squared. 1 over 1 plus r squared. Well, considerably simpler. Now let's take a look what I did here. Right? dx dy became r dr d phi. This integral doesn't depend on phi, and so I took it all out, and here it's just an operator of integration with respect to phi, then an operator of integration with respect to dr. So we have an r in here. So let's take a look at this inner integral first. So it is an integral from 0 to 1 r dr over 1 plus r squared. Well, to you by now, it should be quite obvious how to take this integral. We should make a substitution. So, I don't know, u equals r squared, and then du is 2 pi r. U of 0 is 0, u of 1 is still 1. And so that is an integral from 0 to 1 with that 1/2 in front, and that is du over 1 plus u. Right, so du is 2r dr. If we put that here, 2 will cancel, and we would get our integral back. Okay, so that's a log 1/2, then log 1 plus u from 0 to 1. At the upper limit, this is log 2. At the lower limit, this is 0. So this is log 2 over 2. And that is just the radial part of the integral. But notice this doesn't actually depend on phi. And so when we integrate that with respect to phi, we will have just 2 pi. So the answer is 2 pi times log 2 over 2 pi log 2. So without much effort, we have taken the integral in polar coordinates where it would have been much harder in Cartesian. So the way to proceed is replace the volume element, find out the limits, do the substitution in the function, and then just take the double integral 1 by 1, because more often than not it will just separate into two ordinary integrals. Right, so these are polar coordinates. Let us take a look at cylindrical ones. Again, we need to build the Jacobian. We need to take its determinant, and that connects dx, dy, dz, then to dr, d phi, dh for the cylindrical coordinates. So I will remind you that x was r cos phi, y was r sin phi, and z was just z in cylindrical coordinates. So the Jacobian matrix will be dx by dr cosine phi, dx by d phi minus r sine phi, dx by dh, x doesn't depend on h, 0. dy by dr sine phi, dy by d phi, r cos phi, then y doesn't depend on h. And then dz by dr doesn't depend on r, 0. dz by d phi doesn't depend on phi, 0. dz by dh, 1. And so you can see it reflects the fact that essentially we inherited one Cartesian coordinate here. And the reason why this is so, let's finish the determinant and then I'll draw you a schematic. So then it follows that dx, dy, dz is, okay, let's calculate the determinant of this. It's that, so r cosine squared this plus 0, then 0 minus that, so r sine phi is a square, and then that is 0, and that is 0. So this is actually exactly the same. It's r. Now, here. This appears to be identical to the dh, to the polar coordinate system. So that is also times dh. There we go. This is identical to the polar coordinates, and the reason for that becomes clear when we actually draw the little volume element and take a look at how it transforms as we are moving it around. X, Y, Z. Let us think about it. If we have our dh or dz, it will be movement from here, let's say, to here. So this is our dz. And also dh. Then if we do a d phi, then it's from here to here, and from there to there. So this opening is d phi. And finally dr will be from about here to about here. So we can actually now draw the little volume element that we have. It looks like this. So this is our cylindrical volume element. As you can see, it's essentially Cartesian with respect to dh. If we translate it around vertically, it doesn't change. But if we translate it radially, then it does. And so it stands to reason that it should be the same Jacobian as for polar coordinates, because the third coordinate here is effectively Cartesian. Okay, so let us take some complicated integral in this. Our next example would be to integrate what have we got? F, x, y, z equals just y, so simple, over a fairly complicated region. The volume closed by 3 surfaces. Z equals x plus 2, then x squared plus y squared equals 1, and x squared plus y squared equals 4. Well, before we even begin, we need to find out what the integration volume actually is, and we will need to decide the limits. So that is a plane that these two are cylinders, and that becomes clear if we just draw that. So once again, you can see this integration business rather trains your artistic skill as well as your mathematics. X, Y, Z. Let's have a good think about what we are looking at here. X squared plus y squared equals 1. It's a circle. It's a circle of unit radius in the xy plane. And h is not constrained, so h can be anything. Right? So if that's a circle in the xy plane, when we include h, it becomes a cylinder. So we have a cylinder of the unit radius with the base in the xy plane. It goes up and it goes down. So that's that. That is a cylinder of radius 2. Remember, x squared plus y squared equals r squared. So there's another cylinder here with radius 2. And then this is z equals x plus 2. So if that is 2, and it has to be because this is a cylinder of radius 2, so that is 2. There is a minus. Then this is a line that rises in the xz plane like this. And then y is not given, y can be anything, so this is actually a plane. If I draw that, it will be like a book that is opening up, like that, and then we can bring it down here and then here. So that is a surface. That. So that drops down there, and that drops down there. And then our cylinder is cut by this surface. It rises up, and there are the corresponding two circles up here. So I will draw the top of this. There will be top of it, like that, and then the other one like that. And then our actual surface is between this and that. So that is a bit hard to see, I suppose, by now, but this is like a donut that has been sandwiched in a book. Right? Not that you'd actually do that ever, but we now must integrate over this strange sandwiched donut. Let us think about what the limits are going to be here. Well, we must start at radius 1 and end at radius 2. So in, for example, this radial direction, this is the area with respect to radius that we must integrate. Then all our angles are unrestricted, so we can go around full 2 pi, no problem. And then we must start in the xy plane and end at this surface. Okay, so the integral with respect to phi is straightforward. Integral from 0 to 2 pi d phi, full circle. Then it's an integral with respect to r is from just 1 to 2. Integral from 1 to 2. And I'll put the volume element in there. r, r. And then let's look at the integral with respect to height. It is clearly from 0, but then it will hit the lid, the cover of the book. So our h must terminate at x plus 2. But x is r cosine phi, so this is r cos phi plus 2. Then dh applied to the function which is just y, and therefore r sine phi. Okay, well that's the integral that we must take, and let's see what happens. Just see if I haven't made any arithmetical mistakes on this. No, this is perfectly fine. Okay, so the first step is this doesn't really depend on h. So let's take the inner integral first. Integral from 0 to r cos phi plus 2. It's really simple. R sine phi dh. Well, this doesn't depend on the integration variable, can be taken out. So r sine phi integral from 0 to r cos phi plus 2 dh. So that's just the upper limit, basically. That is r sine phi, r cos phi plus 2. So that's our integral with respect to h finished. Let us take the second integral. Well, let's rewrite what we have left. It is an integral from 0 to 2 pi d phi. An integral from 0 to 2 r dr applied to r squared sine phi cos phi plus 2r sine phi. We could in principle integrate this with respect to r, and it will be a fairly straightforward polynomial. But let's think about what this integral is with respect to phi. Our functions here are separated. There is no r inside phi and there is no phi inside r, so we can take these integrals in any order. However, that is an integral over a complete period. In this case over sine, and so the integral of sine phi over 0 to 2 pi must be 0. It's a periodic function. The same goes for this. This is just a sine of a double angle. So actually the angular integral here is 0 for both this and this. And so we don't even need to take the r integral. We could have taken it, but it would have just become 0 anyway once we've taken the phi integral. And so after a little bit of philosophy, we conclude that this is 0 because the angular part kills it. Okay, so this is cylindrical coordinates. Now the really tough part, the one that I think is the most important, and the one that tends to cause the most difficulty in practice, are spherical coordinates, for which we have two angles and a rather non-trivial Jacobian, which we will now obtain. But first, let's take a look at what we would expect for a spherical element of volume. So if we have our Cartesians again. Now we begin at the origin, and let us carefully draw the different increments in here. So we would have that, and this is our d phi. Then we would start somewhere here and drop our d theta. So that would be here to here, and from here to there. So that opening is our d theta. So let's say from about here here to about there and there. So this there is theta. And finally we have dr, and that will be there. And that is our little volume. When we move this out by dr, so that is dr, two things increase at the same time. It gets deeper and it gets wider. So we probably expect the volume element to be proportional to r squared. But then also look at the theta. If we are to tilt this towards the xy plane, we would have it become bigger. If we were to squeeze it into the z-axis, as you can see, it would become narrower. And then the projection on the z-axis is a sine of theta. And so it looks like it's growing when we drop it, and it looks like it's squeezing. So we sort of expect it to be a sine theta with a question mark. So let us see if we now obtain what we expected. Now, it would have been one thing if I just derived that with horrible formulas, but visualization here really helps to see what is exactly that is going on. Okay, spherical coordinates. X is r sine theta cosine phi, y is r sine theta sine phi, and z is r cosine theta. Our Jacobian will be dx by dr sine theta cosine phi. Dx by d theta r cosine theta cosine phi. Dx by d phi r sine theta with a minus sine phi. Then dy by dr sine theta sine phi. Dy by d theta r cos theta sine phi, and dy by d phi r sine theta cos phi. dz by dr cos theta, dz by d theta minus r sine theta, and dz by d phi 0. The determinant, as you can imagine, is going to be horrendous in here, but once in your life you have to do that. Determinant of k is. That is 0. We have a product of this, this, and this. We have r squared cosine squared theta sine theta. And then cosine squared phi. So this is this triangle. The other triangle with a plus remains with a plus because of these two minuses. It is r squared, then sine cube theta, and sine phi, sine squared phi. Okay, on the counter diagonal, we have that. Would have been with a minus, but we have a minus in here, so another plus. Then r squared. You can see r squared is making an appearance everywhere, so we were probably right in that. Then sine theta, cosine theta, so cosine squared theta, sine theta, and sine squared phi. That's this. that part is 0, and that part again comes with a plus because of this minus. So r squared again. Okay, r squared sine theta sine cube theta. And then cosine phi, cos squared phi. Right, well, it is clear that we have in here something we can take out of the bracket. In all cases, r squared, and all of the terms have at least one sine theta. Sine theta here, sine theta here, sine theta here, and sine theta there. So out of the bracket, r squared sine theta. And then inside the bracket, let us see what is left. Cos squared, plus in here, sine squared, then here cos squared, sine squared, and there sine squared, cos squared. Let's imagine we take cos squared theta out of the bracket. We will have what remains, cos squared plus sine squared. This would be 1. We take sine squared out of the bracket, sine squared plus cos squared, 1. And we are left with cos squared plus sine squared with respect to theta. Again, 1. This entire curly bracket is equal to 1. And so we have r squared sine theta. A bit of a cheating because I knew the answer. But you can see how the geometric sense in there helps us visualize what is going on. And therefore, dx, dy, dz in spherical coordinates is r squared sine theta dr d theta d phi. That's the hardest one to remember and also the most important one because things like the hydrogen atom have spherical symmetry. When we deal with the hydrogen atom eventually, these are the coordinates that we are going to use. And finally, let's take some horrible integral over a sphere, over half sphere, just to make it trivial and illustrate these transformations. Spherical coordinates are also slightly unpleasant because this point where theta is equals to 0, is a singularity in some sense. When you do differential equations in spherical coordinates, it tends to bite you. A few space agencies have lost a few satellites over incorrectly programmed rotations because they couldn't maintain the orientation in the sun. Okay, example. Integrate f of x, y, z equals 4z over upper half sphere of unit sphere. Well, what is the upper half of unit sphere? Phi goes around, r goes from 0 to 1, and theta goes not from 0 to pi, but just from 0 to pi. So the integral is going to be from 0 to 1, r squared dr, from 0 to pi by 2 sine theta d theta, and from 0 to 2 pi d phi of 4z, so 4r cos theta. That's it. So you can see I've separated the Jacobian, so I put r squared under the r part of the integral because it wouldn't be necessary until we get there. Same goes to theta, so that's your r squared sine theta. That's your dr, d theta, d phi, and that's the function you're integrating. Okay, so for the purposes of the phi integral, this is just a constant, so we basically just times it 2 pi. So we are left with 2 pi integral from 0 to 1 r squared dr. Then the integral from 0 to pi by 2. Okay, that gets interesting. So 4r cos sine, 4r cos theta sine theta d theta. Easy to take because that's the sine of a double angle. So integral 2 pi in front, 0 to 1 r squared dr. And I'll take that r out as well just for good measure, so I'll make r cubed. And then that's an integral from 0 to pi by 2 of twice the sine of a double angle. 2 sine 2 theta d theta. And that is 2 pi integral from 0 to 1 r cubed dr. And in here, okay, so that will be a cos 2 theta from 0 to pi by 2. Cos 2 theta at pi by 2, cos pi is minus 1, cos 0 is 1, so minus 2, so minus 4 pi. Minus 4 pi, and then an integral from 0 to 1 r cubed dr. Now that's a positive function over upper half sphere. Where have I lost the minus? Oh yes, of course, integral is minus cos. So it's plus 4 pi. See, common sense tends to save you if you apply it. Okay, so r force over 4 from 0 to 1 pi. And that, I think, is the first year that I ever got this integral right without that arithmetical mistakes. Okay, so that's your integration, and once again we proceed first by drawing the upper half sphere, realizing that our r limit is from 0 to 1, our phi limit is all around, our theta limit is from 0 to pi by 2. So, in the operator notation, integrate from 0 to 1 with respect to r, having multiplied it by r squared because of the Jacobian. The result of an integration from 0 to 2 pi times sine theta d theta, and the integral from 0 to 2 pi d phi. So that's our function. First integrate with respect to phi, then multiply by sine, and integrate with respect to theta, then multiply by r squared, with respect to r operator notation. We could have written it as a triple integral here. It would have been like that from 0 to 1, from 0 to pi by 2, from 0 to 2 pi, and then the content would have been 4r cubed sine theta cosine theta d phi d theta dr. So that's another way of writing exactly the same integral. So take the inner, finally take the outer, so outer. That would have been mine. Okay, so summary of the lecture. Unlike the Cartesian volume element, cylindrical, polar, and spherical volume elements are not the same everywhere, and so dx, dy, dz gets transformed into dr, dphi, dh with something in front to account for that difference. And this really helps us evaluate integrals of functions that are integrals over domains that are easier expressed in those coordinates rather than Cartesians. And the principal use scenario for that is all sorts of atomic physics. Any questions?